Hello everyone, and welcome to our series of webinars featuring tips and tricks for Autodesk Inventor. My name is Dan Williams, and I'm a Manufacturing Applications Engineer for Repro Products Incorporated. Today we're going to be talking about some topics that I found particularly useful but rarely get addressed in training. First, we will consider skeletal versus table-driven modeling. Both are techniques which allow the designer to share parameters across multiple parts and assemblies. That way, if a design or project-wide parameter changes, all of the dependent parts and assemblies update. When paired with Autodesk Vault's copy design, both techniques provide a powerful basis for configuration management, or for what many refer to as engineer to order. Next, we will talk about a number of topics related to how we might control the position or configuration of subassemblies within the context of a larger assembly. Flexible and adaptive are properties of subassemblies that allow the modeler to overcome the default behavior of Inventor, and that it treats subassemblies as if they were frozen, ignoring their internal degrees of freedom. Positional representations provide the designer an option to define noteworthy index positions or configurations of assemblies. We will look at how these can be used again in the context of a larger referencing assembly to define index positions for that assembly. Also, how positional representations can be utilized in the creation of a special type of drawing called an overlay view. The two distinct modeling techniques, often described as skeletal or table-driven, have as their basis the sharing of common parameters between multiple parts or assemblies. That way, if certain of these shared parameters change, all of the dependent parts and assemblies update to reflect those changes. Let's take a look at the parameters of this clevis part. Here we have demonstrated three different types of parameters. The parameters you see here are probably among those you're already familiar with. Model parameters, of course, being those that are the result of just simply placing parametric dimensions in your model, and then user-defined parameters. I wanted to point out reference parameters because these will be featured in a future tips and tricks video. However, all these parameters have something in common in that they're only available to the current part. What we really want to focus on are the parameters associated with this link button down here. What this link button allows us to do is to link to an external resource or definition of parameters. We can link to either an Excel spreadsheet or another part or assembly. Well, obviously, if we're linking to an external spreadsheet, that's probably going to be the basis of table-driven design. If we're linking to an external part or assembly, then that's the basis of what we call skeletal modeling, where a single part or assembly controls all the other parts in the assembly. Let's take a closer look at the Excel spreadsheet that we're going to attach to this drawing. It's a fairly simple format. In the first column we'll have a list of parameter names. The next column will be a list of values. The third column will be units. And then the fourth column is reserved for some sort of a description of the parameter. Now we want to point out that the first parameter name is located at cell D8. This is going to be our start cell for when we link the Excel spreadsheet to our part. The reason that's significant is because Inventor ignores anything above and to the left of that start cell. What that means is that we can use it for things like column headers, but we can also use diagrams, exotic math, pretty much anything that we can insert into a Excel spreadsheet we can position above and to the left of that start cell. Also, if we skip a row, Inventor will ignore anything below that blank row. So again, we can use the space beneath that blank row to perform exotic Excel functions and that sort of thing in order to sort of design intent into our model. So now that we've got an Excel spreadsheet, what we want to do is we want to link it. Again, D8 is our start cell. Once it's linked, you can see that we have a number of additional parameters here. And what's left is for us just to use them. So let's do that. I'll go ahead and edit the sketch of our extrusion. Make this parameter equal to a parameter called clevis gap. We'll make this parameter right here equal to a parameter called clevis thickness. The hole diameter will actually set equal to another parameter called hole diameter. Now that this part is tied to the Excel spreadsheet, if we modify that Excel spreadsheet, say change the clevis thickness to a value of something like 1 and the clevis gap to something like 6, save the Excel spreadsheet. Back in the Inventor file, we can see that there is a pending update. If we execute that update, we can see that the model updates. So now what we need to do is we need to reference this part into a larger assembly and then link more parts to that Excel spreadsheet. So what I'll do is I'll go ahead and start a new assembly. And then I'll reference my clevis part into it, grounding it at the origin. And then within this assembly, we'll create another component. We'll call this shaft. And it, of course, will be a standard English inch part. It'll begin with just a circular cross section. Now, here's where we want to begin to build some dependency between the two parts. At this point, this new part doesn't have any of those common parameters because we've yet to link it to that Excel spreadsheet. So I'll do that now. Remember, the beginning cell was D8. Now that we have our common parameters, now we can place a dimension and set it equal to one of our shared parameters. Now we'll extrude it about a midplane. Again, a distance dependent on one of those shared parameters. And then create some interface geometry. Let's make this equal to the hole diameter. And extrude at a distance equal to the clevis thickness. And then we'll simply mirror that to the other side. Now we can constrain it to the other part, and I'm going to use my Alt-Drag method to quickly apply an insert constraint, so that now both of these parts are dependent on the same table. If I were to modify the table, say make this equal to 0.5 and make the clevis gap equal to 8, save the Excel spreadsheet. Notice there's a pending update, and of course both parts update, because they are in fact both dependent on the same shared parameters. Now let's take a look at an example of skeletal modeling. Remember, the difference between table-driven design and skeletal modeling is basically where the external parameters are stored. Obviously, in a table-driven design, that's an Excel spreadsheet. In our example of skeletal modeling, that's going to be this part right here. In fact, sometimes we refer to this as the skeletal model. If I take a look at some of the parameters I've predefined in this part, you can see I've defined some overall parameters like width and depth. And then I've also defined this thickness right here. That's important because I eventually intend to create some sheet metal parts for this assembly, and thickness is a parameter that's always utilized by sheet metal parts. So this thickness will eventually end up being the thickness of my sheet metal parts. Also notice that over here I've exported some of these parameters. Now the result of exporting these parameters is really twofold. One is that it becomes metadata associated with this part file, but it also makes it available so that it can be browsed by and referenced within other parts. I'll go ahead and say done here. And then I'll begin creating some new parts that I will make dependent on this part right here. I'll go ahead and create a new part. And this is, of course, going to be a sheet metal part. I don't need this sketch, so I'll go ahead and exit the sketch and delete it. And one of the ways that I can reference the parameters of another part into my part is by deriving a new part based on my skeletal model. So I'll go ahead and derive a new part, and I will select my skeletal model. And what I'll do here is I'll go ahead and create something called a work surface. Now, a work surface is particularly useful for creating assemblies that are made up of sheet metal parts and or plate, and you'll see why shortly. Notice that I can also import a number of other aspects of that skeletal model. Obviously, one is the solid body itself, but I can also import some of the parameters. And remember, some of these parameters I exported, so they're already available and browsable. Here's the user parameter for thickness that I'll eventually use to create my sheet metal parts. I'm pretty happy with this, so I'll go ahead and say OK. I'm going to go ahead and select what I think will be a good view. And then I'll use a special technique for creating parts. I'm going to actually thicken one of these work body faces. So I'll go to my 3D modeling task, and then I'll thicken this particular face. I want to make sure I thicken it to the outside. That's good. And I'll go ahead and make that a distance of thickness. Remember, that's the shared parameter that was predefined in the skeletal model. So I'll go ahead and say OK here. I'm pretty happy with this part. Eventually, I won't need this solid body or work body to be visible, so I'll go ahead and turn off its visibility. I'm going to save this file as, we'll call it right panel. And then as a shortcut, since the same process is going to be utilized to create the rest of the parts in this assembly, I'm going to go ahead and save this file as left panel. And then I simply need to delete this thickened feature. I'll temporarily turn back on the visibility of my work body, thicken the opposite face, again a distance of thickness. In my final part, I won't need to be able to see that work body, so I'll turn off its visibility. Save the file. And then save it as a third part. This one's going to be called top panel. top panel, I don't really need to see this thickened face. I will need to temporarily be able to see the work body though. This time I'll thicken these three faces here. Again, thickening all to the outside, a distance of thickness. In the final part, of course, I don't want to be able to see this work body, so I'll turn off its visibility. I am pretty happy with all of that, so I'll go ahead and save this file. Now what I can do is I can start a new assembly. A standard inch part. The first part I'll place will be that top panel. Now, one of the advantages of creating parts in this fashion is that they all share a common origin. So as I place them, I don't need to bother with actually using any assembly constraints. I can just ground them all at the origin. Because they all have the same origin, they'll all be inserted in their correct location. Let's do the right panel now. Again, grounded at the origin. Repeat the process for the left panel. Grounded at the origin, and I have a nearly complete assembly. Now, this was a slightly more complicated example of creating parts within a skeletal model because it used that derive part functionality. You can actually utilize it in a much more simple fashion by placing any component and then just linking it to the part in a fashion similar to the way that we linked parts to the Excel spreadsheet in the table-driven example. So now if I, for instance, place a component from Content Center, let's just go ahead and place a ANSI equal angles piece of angle, and we'll make it 2 by 2 by 3/16, and we'll just give it some standard length for the time being. We'll call it 12 inches. Obviously we want it to be a custom part. In this case we'll call it brace front. So as I place this part, it just has a unit length, for instance. What I want to do is to make sure that it's always the same length as one of these sides of the part. So what I can do is I can determine what was the parameter that controlled that length. If I go back to my extrusion and edit sketch, I can see that that's actually width. So back in my assembly, I'll edit this part, and as you know, structural steel shapes from Content Center have a parameter called base length. So this base length is what I want to make equal to the width of my skeletal model. So I'll just go ahead and link, this time apart, our skeletal model to the structural steel shape, and I'll make sure that I use this thickness, I'm sorry, not the thickness, but rather the width as the parameter. Notice now that we have a width parameter that I will use to control the base length. Now you can see that the base length of our structural steel shape is equal to the width of our skeletal model. So if I go back up to the top level of the assembly, and we'll just quickly create some assembly constraints here. Again, I'll just use my alt drag method to quickly quickly apply a few assembly constraints. Let's edit that constraint, make it a flush. Alright, so now we have a somewhat complete assembly, and as you would expect, if I go back and change some of the parameters in my skeletal model, say we'll change the width to 48 and the base height to 72, with the vent diameter now being 20. You can see we have a pretty radically different skeletal model than we had before. If I return to my assembly, I see I have a pending update. If I replay the model, you can see it updates and all the parts update appropriately. Now I'd like to talk for a bit about flexible versus adaptive subassemblies. I think most of us are aware of the fact that in Inventor, when you have an assembly that has subassemblies, and those subassemblies have some sort of a degree of freedom, when you're at the top level of the assembly, if you try to evaluate it via a constraint-based drag or any other way, Inventor doesn't actually look into those subassemblies for degrees of freedom. Over the years, a number of different solutions have been put forward to this situation. I've even seen people save copies of the subassemblies to different names so that they could specify them in different positions. However, that has an impact on the bill of material, so we really don't want to try to use that as a solution. One solution that's been proposed over the years is a property for the subassembly called adaptive. Now, if I edit one of these subassemblies and I look at the constraint that prevents that cylinder, for instance, from extending and compressing, that's this stroke constraint, notice that I've suppressed it. So one would intuitively think at the top level of the assembly, I should be able to drag this around, but that's not the case. Again, because Inventor doesn't look into those subassemblies by default for any degrees of freedom. So if I were to take that cylinder, or any one of these three cylinders, and give it the property adaptive, essentially what I'm telling it now is that Inventor should look inside that subassembly for degrees of freedom. And in fact, I can drag the assembly, but you'll notice that every one of those cylinders has to be in exactly the same position. Let's go ahead and look at a little bit simpler example of that. I want to turn off adaptivity here, and I'm going to create a new subassembly. Just use a standard inch assembly. And in that subassembly, I want to take one of those cylinders and just instance it. Now in this subassembly, I'm going to go ahead and instance one more copy of it, and I'll ground it. So notice that when I go to place the first cylinder, or actually give the first cylinder the property adaptive, as I manipulate its position, both cylinders, or both instances, are basically identical. That's kind of a problem in an assembly like our arm assembly here, because in real life we would want each of those three cylinders to be potentially in a different configuration. There's another limitation to adaptive in that only one instance of the cylinder assembly can be adaptive anywhere. In other words, now that it's adaptive in this assembly, I couldn't go back in this assembly right here and make another instance adaptive. It just doesn't work that way. So there are obviously some limitations to adaptivity. I'm just going to go ahead and start over again, and this time I'm going to look at making both of these subassemblies flexible. Now, notice that I can make more than one instance flexible. That's encouraging. And now that both of these instances are flexible, notice that I can position each of them independently of the other. So let's go back to the original assembly and look at the example where we make one of these adaptive. And notice that we really only have one type of motion we can describe here, where all three cylinders are in exactly the same configuration. But if we turn off the adaptive property for one of the cylinders and then make all three flexible, you can see that we can pretty much describe any position for the arm assembly. And those are the major differences between the adaptive and flexible properties of subassemblies. We just discussed how the flexible and adaptive properties of subassemblies allow us to have Inventor evaluate the degrees of freedom of subassemblies within the context of a larger assembly. But neither one of those solutions really give us the ability to define index positions for those subassemblies. Obviously, there are certain more important milestone index positions for subassemblies that indicate range of motion and things like that. And positional representations are really a good solution for that. If we look back at our assembly again, notice that when I go back and re-enable that stroke assembly constraint, and I right-click over it, there is an option missing right here, and that option only becomes available if I create a positional representation to accept it. So here in the cylinder itself, I'm going to create a positional representation, and I'm going to call this new positional representation compressed. And I'll create another positional representation. This one I'll call extended. Now that I've defined some positional representations beyond just the master positional representation, if I come back down here to the stroke assembly constraint, notice that I have an extra option here now. Well, if I select a specific positional representation and make it current, and I can come down here to the new option and define a new position for that assembly at that positional representation. In this case, I'm going to say the extended position is at 150 millimeters. Now I'll activate the compressed positional representation, and I'll say that at that position the assembly constraint should be equal to 0. So that now I can toggle between extended and compressed for each instance of that subassembly. So what the positional representation actually captures is some combination of assembly constraint overrides. I can actually have multiple constraints overridden per positional representation. Something else that a positional representation can capture is the combination of positional representations of subassemblies in an assembly. So I can actually go up to the top level of the assembly and create 3 new positional representations. One we'll call down, another we'll call up 1. I'm slow double clicking on these to rename them. And up 3, or up 2 rather. Now that I have positional representations, I'll activate the down positional representation, and then go to each of the cylinders and select the positional representation I want to use for the down positional representation of the top assembly. So for each of these, I'll select the compressed positional representation. And then for the up 1 positional representation, cylinder 1 will continue to be compressed. Cylinder 2 will be extended. But cylinder 3 will continue to be compressed. Finally, for the top assembly positional representation up 2, all positional representation for cylinder 1 will be compressed, and then for cylinders 2 and 3 will be extended. So that now I can describe 3 different positional representations for the top level assembly. One application for this is the creation of something called an overlay view. So I'll go ahead and start a new drawing. We'll use an ANSI inch drawing. And in this drawing, I'll go ahead and create a base view of our assembly. Let's use quarter scale. And for our positional representation of the base view, we'll use down. Now I can mouse over that view till the view border highlights, right click, and create an overlay view. In this overlay view, I'll use the positional representation up 1, and I'll repeat the process to create another overlay using positional representation up 2. And in this way we can describe ranges of motion. We can even dimension between different positional representations. So you can see how useful positional representations can be in describing index positions for assemblies, and how flexible versus adaptive subassemblies offer 2 other options for sort of reaching down inside of subassemblies and evaluating them for their degrees of freedom. Thanks again for joining us for this Inventor Tips and Tricks webinar. If you found anything useful, if you'd like more, then certainly we'd like to hear from you. You can contact us at www.reproproducts.com. Also, you can follow us on Facebook, LinkedIn, Twitter. My name is Dan Williams. I'm a manufacturing applications engineer here at Repro Products.